our focus is really on system issues. That's really what we think we are good at. Our background is in power system, but we don't want to stay just in power systems or dealing with the traditional power system. One of the things we want to do is to, and Anjan has already very much started doing that, is bring in some colleagues who specialize in communications, colleagues specialize in cybersecurity, people who have experience in large software systems, colleagues doing optimization, or data-driven systems, or sensors and sensor integration. We want to bring all those people to the party and help work on the system, taking all those aspects into account. And we see ourselves as trying to provide a bridge between these disciplines towards and applying them to the power systems. So, system is a focus. What are the various directions that we could take or we plan to take? The first direction is architecture. Lots of things are changing. You know, the architecture of the grid itself is well established, but if we bring in a lot more communications, all we need to think or rethink how it's all going to work together. Another direction is planning. How do we plan the smart grid? You know, what needs to go into this planning? Operation, well, that's probably one of the areas where the changes are going to be the biggest. You know, it's not going to be operated the same way it used to be operated. And then there are issues in protection, new modes of protections, and obviously new modes of control. And underpinning all of that, we're going to need an awful lot of computation, so there will be lots of big, complicated issues dealing with problem sizes and algorithms for all of those questions. So, in a way, this is fairly traditional, but that's because a system always needs to be designed, planned, operated, protected, controlled, and you always have to deal with the computation. But some of the issues are actually quite different. So what I propose to do now is to take a few examples of research projects that we plan to investigate. And the first one is, you could call it flexibility. It's a term that has already been used a few times today. And one question there is, how much flexibility do we really need? Now, it's commonplace these days to say, well, because of the wind and the fact that we don't know when the wind is going to blow, when the sun is going to shine, the system is going to be more flexible. But providing flexibility costs money, so we don't want to provide more flexibility than we need. So we have a complicated problem to figure out exactly how much flexibility do we need. Another point, and has already been touched upon this morning, some of this flexibility can come from physical resources, like demand response, like storage, or simply by having power plants that are more flexible. But some of this flexibility can also be virtual flexibility coming from a more dynamic way of doing scheduling and operating the system, or more flexible rules in the way we handle the system. Another question is, taking another perspective, the perspective of somebody who wants to invest in flexibility resources. Well, they may want to say, well, what's the value of my resource? Or what is the value of my resource to the system operator? What can I sell it for? Do I have a viable business proposition here to invest in this flexibility resource? And if you go back to the other side, the system operator's perspective, you could say, well, what portfolio of flexibility resource is optimal? They don't all have the same characteristics, so what mix do I need? And again, from the system operator's perspective, you probably don't want to have all those resources in your own portfolio, so you may say, well, what incentive do I need to give to different stakeholders so that they are going to invest in resources that provide me the flexibility that I need, at the same time I don't want to give them money that they don't deserve, so where do I stop? And then an issue that we already discussed, I think, a bit between Hardev and Steve earlier. Should this be done in a centralized manner, where the system operator decides what flexibility is needed and schedule this flexibility and so on? Or do we push the responsibility back to the people who cause the need for flexibility, essentially tell the wind farms, if the wind is going to go up and down, well, you have to take care of that yourself to make yourself more predictable. So all of these are issues that we can describe as relating to flexibility. Demand response is quite an important thing. You know, the demand response can mean different things, depending on the time scale you're talking about, depending on what you're asking the consumer to do. So the consumer could actually provide different types of services to the grid, and we need to understand better what services can be provided and at what cost those things. And then if we have these services that the consumer might be able to provide, well, how can we harness them without inconveniencing the customer? And then we are back to the studies that Pat Hoffman was mentioning this morning. And also, we are getting all these smart meters that are going to collect vast amounts of data. And assuming that we don't decide that the consumer owns this data, maybe we can learn lots of things from looking at this data. And we can possibly use this information to better run the grid. I recently been struck by the fact that we know very, very little about the demand at individual level. We know a fair amount about the aggregated demand. We can do forecast quite well if we aggregate enough. But if you go down to a consumer or a group of consumers, we know very little about what their demand is and how it might be able to change. Next topic is IT infrastructure. We have the grid. We have lots of communication technologies. What is the best way to match the two? How should we specify the communication network to work best with the grid? And there's a bit of a chicken and egg question there, because we can't really decide what application we're going to run until we know what communications we have available, and we don't really know what communications we need until we know what applications we want to run. So that's always a tough one to answer. Other issue there is vast amounts of data, much more than we have dealt with before. How are we going to manage all of that? And also, should we stick with the current paradigm where the applications are run centrally, or can we design the infrastructure in such a way that some of these applications are run in much more decentralized or distributed manner? Next is uncertainty. That's another buzzword that keeps popping up, but I think we need to know, as good engineers, we should say, well, how much uncertainty is there really? Can we quantify it? And also, probably more difficult question, what's the correlation between the various random variables that are out there? Because until we can answer that question, we can talk a lot, but probably not design very good solutions. And in power system operation, we like deterministic security criteria. They are wonderful in a sense because they suit everybody. They suit the operator because they can say, I've done my job if there's a problem. They are simple, they are easy to calculate. But if you look at it, they don't really reflect the actual level of risk. And if the uncertainty level is going to increase, really what we're interested in is having a level of risk that we find acceptable. So my view is deterministic security criteria are simplistic, and we have to look at things in probably a more probabilistic sense, which is not necessarily something that's going to be easy to accept. Another point is, if the world becomes more uncertain, if the uncertainty keeps on growing, trying to handle things just with preventive security measure, is going to get ridiculously expensive. And so it's much more, there's going to be a push to say, well, can we just react to events when they happen while still maintaining the reliability of the system? But then the question is, how much corrective action capability do you need, and can you be sure that it will be available when you need it? Next is wide area control and protection, and there the picture, I have to say, is I've borrowed from two groups of people in the Adrian Schweitzer lab and BPA, because I found it's a beautiful illustration of those things that could be done. Wide area protection and control it's a wonderful idea, and some people have designed some really clever schemes. But there are not a lot of them out there, and the reason is because we don't have a standardized methodology. We don't have a standardized way of doing things. Most of the time it's done on a case-by-case basis, requires a lot of engineering time and talent to do it. And also, every time, periodically you have to go and revisit and redesign them because the system has changed. If we can develop a way of standardizing the way we put those wide area control and protection in place, we might be able to do them much more often, much more reliably. And if we are able to do it in an easier way, we might be able to push it down to lower voltage levels and have it in more places, and therefore run our system in a more efficient and at the same time more reliable fashion. And one area that's of particular interest to Anjan, in fact, is we have some good algorithms to optimize voltages over a wide area. The question is, how do we go from the solution of this optimization calculation to an actual implementation, adjusting the voltages over this wide area, optimizing the economics and at the same time the security? Then we have had analysis and design tools for the power system for a long time. But if we're going to have a system that relies a lot more on communication and control, our design tools are going to have to look not only at the traditional power engineering, power flow, fault calculation things, we're going to have to include the effect of the communication in the way the system operates. We're also going to have to be able to perform tests that involve both hardware and software. And all of that is going to have to integrate the demand response. So that ties back to another of the ideas where we need to know much better what the demand, how the demand behaves. We need to understand the demand so we can model it better in these tools. And finally, I'll leave you with maybe something that's a bit more futuristic. You know, the paradigm we have been using for the last 100 years is that we have to match the load and the generation on a second-by-second basis. Well, DOE is putting a lot of money, and other countries are also putting a lot of money into research, into storage. And it tends to be looked at on a global basis, kind of ignoring the network. But if storage, or when storage, becomes cost-effective, we could imagine having storage distributed in various parts of the network. And in a way, just like communication world was revolutionized when we went from analog communication where you needed a physical circuit for the telephone calls to happen, to a digital world where we could use digital buffers, buffering the communications that it went on in a way that was transparent to the users. We could use this distributed storage to pre-position the energy close to where the consumer is going to need it. And also, that would allow us to use that energy in different ways if we have an emergency somewhere in our network. So it's looking at the same time at not just at the issue of storage, but also at how the storage might interact with the network. Another way of looking at this is to say, well, there's more and more opposition to building new transmission lines. If we get to the situation where we just can't build some transmission lines, we will have to use this mode of operation. And so one of the questions is, when does this mode of operation become practical? How cheap does storage have to become for this to be a viable proposition? Or another way of saying, how much carbon tax do we have to put in to make it happen? Then we need to refine the concept and develop the tools to decide how we can operate in this mode, this package switching energy networks. And then obviously we need to have tools to design where do we put this distributed storage, and how much should be available at different locations. So that's a brief overview of some of the research ideas that Anjan and I have at this point.
The next speaker is Karl Imhoff from PNNL. He is in charge of the electric infrastructure sector of PNNL. And I think the thing that maybe you wouldn't know from reading this bio is that he's been instrumental in building up the largest power engineering research group among all the national labs. Every national lab, and some of them more well known than PNNL, can I say that? Claim that they're doing research in the smart grid and in the energy space. But if you look at the activities and the numbers of people and so on, PNNL leads the pack to the point where I think people like Patricia Hoffman use them as resources at the national level. And I know for a fact that our congressional delegation, who are very interested in the energy picture, have used his group and him and his group to a large extent in setting some of the policies. Karl.
Thank you, Anjan. Thank you, everybody. It's a pleasure to be here, and really pleased to have Daniel joining the club. I appreciate the support from both academic institutions to bring this forum, the symposium together. I wanted to provide a little bit of baseline in terms of what research is going on at PNNL, and talk a little bit about the context. At PNNL, our primary focus is on the national R&D agenda, but we also have a large fraction of our work that transpires here in the Pacific Northwest. We have long relationships with many of the entities represented here in the room as well. And I think part of what we would like to offer to the activity, both is to participate in research, but to provide a bit of a two-way conduit. One, to help connect what's going on here in this region to the national agenda, and also the other way around, help the national agenda be informed by what we're doing here in this region. Very clearly, there are significant regional differences, and the speakers this morning talked about it. We need to do what makes sense, job one, for here in the region. I think that's first and foremost for the symposium. But there are significant synergies from the regional level up to the Western interconnection level and then to the national level. Really those three domains, and we operate in all three of those domains. So I'll talk a little bit about what we're doing at the laboratory. I'll try to inject a few ideas in terms of where we think are the richest opportunities for innovation, where this region can not only be successful for our local agenda, but also contribute to the national debate. So just very briefly, a lot of people don't know what a national laboratory is. I use this slide only to say that our primary focus is on the DOE missions, strengthening the underlying scientific foundations for the nation. So that's a very much longer term basic science focus. Ensuring the adequacy and security of our energy supplies, minimizing the environmental impacts of our energy agenda here in the country, and then also dealing with national security, which in this case translate mainly to the cybersecurity agenda as well. So that's what drives the research agenda. We are there to support the long-term national interest in those areas of energy. Historically, the utility system has done an excellent job of providing affordable, reliable power. That's job one, and it will still remain the fundamental activity of the power system. What's reflected in much of our work at the laboratory is that in addition to that traditional role, we feel that the system will become increasingly important to those national level public goods issues around energy security, reducing oil imports, finding ways to take carbon out of the system that we find as a nation decide as an economic target or goal. And I think these are oftentimes new expectations that will be applied to the grid. So going forward for the next 20, 30, 40 years, the grid, we believe, will become more strategic to the national agenda as on top of the traditional role of affordable, reliable power. So I like to use a very simple schematic that most of you would easily recognize, the fact of how data flows today. At the transmission level, we as a region have provided leadership since the late 80s, early 90s, RDEV, in terms of using time-synchronous data to help operate the Western system. So there's a good bit of transparency and digitization that started. It's been underway for decades. It's nothing new. The grid's been kind of working on that for a good while. We've had a good number of phaser measurement units and DFRs and other things in the West. The distribution system is pretty much standard SCADA system. There are a lot of utilities today who still wait for phone calls to figure out whether they have outages and where they are in their system. And we still have very little data or information flowing through to the customers. I think, and we think, a compelling vision that's not too far in the future is the fact that time-synchronized data, either at sub-second levels or 5-minute levels or whatever the right time slice is going to be virtually commoditized in a very short time. Just in the last 10 or 12 years, looking at the explosion of what we see in the system today, that's just going to accelerate going forward. And I think this provides a foundation for a rich sense of research, whether it's cybersecurity, cognitive scientists, and the cognitive science to translate data into information, communications architectures, everything else. It's all going to be driven by this data. And I think this is a fundamental driver for a lot of the innovation that we can provide, and much of this is going to apply nationally and globally as well. At the laboratory, we divide our research in these following areas, and I'll say if you take away the stimulus funding, we do about $30 million a year of research. About 80% of that is for federal government, and about 20% of it is with private entities and utilities, EPRI and private utilities, et cetera. But these are the 6 main areas that we've divided our research agenda into. First is this notion of system transparency. This notion of commoditized time-synchronous data is going to let us see the system like we've never seen it before. And the question is, so what? My personal observation is about 80% of the effort you see in industry and government and everywhere else is using this new data resource to do today's concepts, today's operational approaches better. And that's great. My point, though, is that's perhaps not sufficient. We can also now, that we can see the system like we've never been able to see it before, look for whole new paradigms of conducting business and designing the system and planning for the system and controlling the system that were not around 30 and 50 years ago when much of what we're operating today was initially designed. Analytic innovations, as you get this data and distributed computing, et cetera, there are a lot of opportunities both from the mathematics side as well as the computational side to dramatically improve the performance to drive almost all the operations we do today down to real time, or no longer do the operations we do today because there are new opportunities for doing things differently. A third area that I'm personally very excited about where this region can contribute is the connection between energy efficiency and the infrastructure, the two-way communication that smart grid investments are driving at places like Avista and Snowpud and many others. We think that we as a region have a 20, 30-year history of leadership in energy efficiency. We have regional institutions, the Power Planning Council and others, who know how to aggregate what are the issues and sort of set those aiming stakes so that the region can determine how to pursue it. And our sense is that you can probably get an extra 8, 9, 10% of carbon reductions leveraging the two-way communication and distributed intelligence and smart grid if you think consciously about those connections between the built environment and the power system. Renewables integration has already been discussed a good bit today, and we do work not only in the region with Bonneville, but also with CalISO and others in the Western Interconnection and with DOE at headquarters. Energy storage we view as a really important new degree of freedom for this more complex bidirectional power system of the future. Daniel talked about it a little bit earlier in terms of getting storage into the neighborhoods and the communities. Our goal at the laboratory is to drive that price point down in half and develop new tools to help us be more precise about. So where's it going to add value? At what point in the system? At what price point? At what performance point? And lastly, cybersecurity has been fundamental to our activities for the last 20 years. And we are behind the federal cybersecurity firewalls. We conduct a lot of cybersecurity monitoring for the DOE infrastructure across the nation. So this is an area of high importance to what we're doing down at the laboratory. We also developed the cybersecurity requirements for the investment grants and regional demos and are helping monitor those and evaluate those for DOE. So that's just a sense of where we're currently playing. This is just a slide showing some of the emerging visualization tools that are being tested in various control rooms and other places around the country. And I think the key point here really is this whole notion of cognitive science and how do we extract information more effectively from this emerging integrated cloud of data. We had the pleasure of hosting the WCC operator training group last June in Richland. And we cut a deal with them. We said, okay, you can do your 3 days of commodity training there if you'll give us a 4th day so we can do a really nice structured human factors experiment to compare some of the new visual techniques that have some advanced computation behind them to the traditional line diagrams that they use in operator training. And we demonstrated about a 30% improvement in their ability to detect and diagnose what's going on and identify the right remedies. The downside was they all said, so how do we get it? And we said, well, you can't really get it yet. We got to work with Jay Geary and Mike Atkinson and the other vendors to help find ways of getting this into some of their tools. There is a substantial investment in the region right now. About $78 million of private capital is teamed up with about $78 million of federal funds to do what is the largest of the national regional smart grid demos. We're touching 60,000 metered customers in 5 states, 11 utilities, a large number of vendors. Alstom is one of the project vendors, as is IBM and Netezza and others. And we're really conducting 2 experiments. Each of the 11 participants is doing what makes sense for them and their consumers and their infrastructure, and whether they're surplus or deficit, et cetera. They're doing what makes sense for them. Many of them are doing distribution automation, they're doing demand response, they're doing energy storage, photovoltaics, large number of things. We even have Seattle City Lights working with the University of Washington, and Avista's working with WSU, and we're going to call it Grid Cup, or I'm not sure what we're going to call it, but I think there's going to be a little bit of competition between the universities and the demonstration. But in addition then to what's going on at the local level, we're working with Bonneville to conduct a region-wide synthetic 5-minute signal that will reflect the requirements for preferred clean generation, issues around transmission congestion in the region, and also issues around the requirements for balancing to help support renewables integration. And so the proposition to test here is, can we find ways to leverage that information architecture, cut across the traditional silos of transmission and distribution, extract value from these new smart grid assets across that silo, and demonstrate value to the region and the regional system as well as down at the local level. So that's the fundamental proposition. It's a very exciting experiment that's underway here in the Northwest. I mentioned this issue of cutting across silos. We've also developed a new open source platform of software that's getting a lot of attention around the nation, but also here in the region, where we look to sort of integrate into a single integrated tool for the distribution system, something we call GridLabD, that merges power system, power flow tools with load or end-use tools with market tools. Now, most utilities have these kind of analytic tools representing each of these 3 domains separately. But this tool is intended to basically let you look at every single end use on a distribution feeder operating in real time, so you can see in high resolution what are the impacts or benefits of demand response and energy efficiency and volt-var optimization and PVs and maybe adding some storage into the distribution system. So the intent here is to provide a new high resolution tool that's in the open source and get it out and getting it use. And I'm happy to say there's nothing more exciting to me than walk in our operations center and see 15 or 20 summer students, many of whom are from these 2 institutions, sitting there working on research in the summer. But we're embedding it into the training grants. We're working with vendors here in this region. It's part of the Northwest Demo. It's part of the national agenda as well. And I think part of the research opportunity is, what is that next generation of tools we need to capture the full value of some of these new concepts that we see before us. Renewables integration, the whole issue of the stochastic nature of renewables and how to handle that, both in traditional EMS systems, improved forecasting, an extremely rich area of opportunity. Energy storage, I've already mentioned. I think our target is we need to drop the price point down substantially, and I think there's some phenomenal materials opportunities for doing that. That's a nice opportunity for some of the institutions in the region to cooperate on. But then from the system standpoint, the issue is, so what if we drop the price in half, so where are we going to capture the value? And that again, I think gets back into the utilities in the room, the vendors in the room, and others. Assuming we can get that price point down in half, how do we use it? Where do we put it? How do we extract value from it? How do we control it? Much of this has already been discussed, but you can't underplay the importance of cybersecurity. And I think the big challenge at the national level, I would argue, to a large extent, we've been kind of playing catch and patch for the last decade. And the question now is, how do we move towards designing systems and control concepts that are inherently more secure? Build it into the design concept. And that raises one fundamental question that we could probably spend a decade, and I think the nation probably does need to spend a decade on. The issue is, now that we are moving to an era where we have observability throughout the system and ubiquitous computing, do we stick with our current control paradigms, or are there better control paradigms we might want to move towards? And that's a debate we really, I don't think, know how to structure. You know, the issue of what might those goals be, what might the benefits be, I think that's a debate that all of us in this room can influence and contribute to, but that is probably a national debate as well. So this whole issue of control and cybersecurity, what is the system we want in 2050 and 2100? And might we be more efficient economically in other ways if we sort of started setting some of those aiming stakes, setting the goals I heard Steve Klein talk about? What goals might we want to aim towards, so that as we're investing today and learning today and communicating with consumers today and innovating in the vendor community and everything else, we might have a little sharper target for where we might be able to take this whole parade 20 and 50 years down the road. That's what personally gets me extremely excited about the research agenda, the innovation agenda, the policy agenda, and the delivery and conduct of how we make electricity an even more important part of what we do going forward. So my final slide. So what's different about our region? I'm reminded of that phrase, we don't need no stinking standard market design here in the Northwest. We have a very high penetration of renewables. I may get these numbers a little wrong, but I think Bonneville's roughly at 3.6 gig, heading to 6. They're about a 9 gigawatt control area and about an 18 gigawatt region. So we're already facing very high levels of renewables penetration. We have a large hydro base where a lot of people east of the Mississippi River seem to think, well, what the hell, you guys got a big hydro system. Well, that hydro system is already way oversubscribed. But those two issues give us a unique approach to how we need to handle and deal with this emerging push on renewables. We have a lot of regional investment and leadership in digital concepts. Many of them are in the room today. Schweitzer, Itron, Alstom Grid are outstanding global leaders in these spaces. Microsoft and Intel and others are in the neighborhood as well. We have a lot of profound innovation assets here in the region that I think give us an opportunity to do something special, not only for what we're doing in the region, but on the global scale. I already mentioned our legacy and efficiency. And we do have policy goals in terms of carbon and other things. Well, because of our hydro system, really, if we're going to do anything with carbon, it's going to be in the transportation sector. So if we're going to pursue carbon, that's going to require electrifying transportation, because we have very little carbon in our power generation here in the region. So where do we want to be as a region in terms of electrifying transportation, and what does that mean to the system we want going forward? I think that's an important differentiator for us. And so I would close with these two questions to kind of stimulate some of the discussion. How can we at the region leverage our innovations at both ends of the spectrum, high and low voltage, to lead grid modernization in ways that engage and delight the consumers? We dare not do this without the consumers. I'd argue we have plenty of technology right now to do incredible things. We just need to get the policy signals through and to make sure the consumers are part of that journey and are delighted by the whole process. And then how do we go beyond just improving the current paradigms of how we operate today to think about what new ways might be way more productive and effective and efficient? And I would point to a really important issue that I think is important, and it's kind of from the national perspective. Much of what you see going on today is focused on the individual balance sheet. Steve is working on what makes sense for Snowpud, and Don Kopczynski's working on the Invista and everybody else. And they also do look at the public good sort of more broadly. But as a nation, I think we are hampered by our ability to figure out, so what's the value of reducing oil imports, and what's the value of improving reliability across interconnections? So those issues of public good sort of at the interconnection level and how they connect to investments being made and what the regulators in Olympia and other places are dealing with in terms of getting the right incentive signals through, I don't think we have that whole chain connected. So I hope that with what we're doing in the region's smart grid demonstration and the Western Interconnection Phaser Project that Bonneville and others are leading, and with the local activities with Snowpud and Avista and other utilities, I mean Benton County PUD and a lot of others are putting in this stuff without any federal funds. A lot of activities going forward, but I think we need to be thinking about what national outcomes do we want this grid, this highly digital, highly effective, highly precise and agile grid, what national outcomes do we want it to deliver, and how do we connect that to the regulatory and policy decisions that are being made at the state levels. So with that, I'll finish.
Okay, so we start the question and answer session, but we'll, in the morning, I'll prime the pump. And ask two of you to respond. And one of the things is that at the national level and even at the regional level, it is easier to ask the question, the important questions, than to actually devise the research programs, right? So if you didn't think of money as a problem, what would be a research program that that you would like to see? Let's say a 5 to 10 year research program. And I'll note that the person in charge of the national level research on smart grid is in the room. So if you're convincing enough, this will be in the 2012 budget, right?
Well, I'll throw one on the table, and there are many that come to mind, but one of the intriguing outcomes we discovered at the Little Demand Response Demonstration on the Olympic Peninsula, 2 interesting facts. We were told by some people that no one's going to want to sign up for that stuff. People don't want to sign up for real-time rates. Well, they all wanted to sign up for it, and we had to sort of push them back to sort of maintain the statistical vitality of it. But we learned something really interesting. We found that thermostatically controlled devices like electric hot water heaters and strip heating, of which we have a really high penetration in the Northwest, just turn on a dime in terms of very subtle signal or incentive signals coming down the 5-minute signal. So we're testing this notion on the larger demonstration of how durable is the potential value of end uses like electric hot water heaters or strip heaters as demand response and helping with ancillary services. And what's the elasticity of that consumer demand? I think we as a region have some unique attributes given the nature of our loads, and we are particularly well suited to demonstrate or test some of those hypotheses in that area of extracting value from end uses, not just for shifting peak, but for also providing ancillary services and other values to the power system.
I think we have, there are lots of solutions out there, and we talked about them already a lot today. I think what I'd like to be able to deliver 3 to 5 years from now is not a blueprint, because a blueprint is printed. You can't change it easily. Let's call it a conceptual spreadsheet that would let you put in the characteristics that you have and change parameters, and then you can assess the value of this solution or that solution, and then you can compare and decide which direction you can go. Where do you want to invest your money? Where does it make sense to invest money for building this grid? Because we have to face it, it's going to be expensive. So this is not the kind of investment that should be done lightly.
Dave Bach in Washington State University. So I have a question for both the panelists. As a computer scientist looking from the outside in for 12 years now, working with Anjan, and one thing that struck me about the electricity sector is, and Daniel alluded to this earlier, that a lot of the control and protection strategies are one-off. Obviously computer scientists have a notion of an algorithm, and we have a piece of logic that does sorting or searching or something. We study it to death. We know how it's going to behave performance-wise and statistically and all this thing. But what pieces of the puzzle need to happen for power algorithms to be more reusable in a broader context? And what sort of research questions or agenda might move? Maybe it's hopelessly, maybe everything is unique, but maybe it can be gotten a lot closer. I don't know. So I guess I'd ask for your comment on the technical subject, but then also what research pieces would have to be addressed.
The answer that comes to mind is that the utilities have achieved an amazing feats of reliability, but it has been done in a very inflexible manner. And I think if we probably need to think more a bit about defense in depth, and rather than applying preventive measures that are very, very powerful but rather inflexible, if we can develop more corrective controls, things that reactions that the system can have, we have a better chance of being able to do that in a more flexible manner than we can do now, and then develop these algorithms that could react to the situation. And if we have more of those synchrophasers and so on, we'll have the information that we need to be able to put that in place. That's the hope, but I think you're right when you say that it's going to be complicated.
Dave, let me take a little cut at the software side of that question. We have a bit of a challenge, and I'm not quite sure how to solve it. The issue of software. Open source software has pluses and minuses, and the upside obviously is you get more people engaged in trying to move towards some standardized approaches or processes. But then that creates IP issues, and oftentimes that's viewed as something that a vendor is a little uncomfortable picking up. And so this issue of reuse and accelerating the cycle, I'm understanding your correction, David. I'm not sure how we solve that, but I think there are people in the room who know a lot more about that than I do, who might have some thoughts going forward about ways we could shorten that time cycle, get more leverage out of new systems or algorithms and code, et cetera, to make that work more effectively. As to the controls, I struggle with that as well. I think that's pretty much a bottoms-up sort of local entity approach in terms of the control activities. And I don't know I don't know what's the right way to change that. I think that my only solution or my only suggestion is that we need to have a structured national discussion on, given that we have sort of transformative new ways of handling issues, we need to structure that debate in a way that can maybe focus research at the academic level, and also look for ways of leveraging things across interconnections to begin doing studies. I know the WEC is doing some interesting work now, looking at adaptive islanding as armed by phaser data, and there are many interesting ways of advancing control paradigms, but we had to proceed very cautiously. We had to find one utility that would be willing to give us some data to do some simulation runs. And then once that looked good, then you have to approach the right subcommittee at WEC and slowly over the course of about 6 months get them to say, well, actually that might have some interesting value, and so we'll consider that. So then you get more data, and now you're moving up towards the WEC-wide. It's just a very slow process, and that's, for a lot of good reasons, it's a very slow process. So, and I'm not sure how we shorten that time cycle. That's a challenge.
It's a point, we don't really have a lab to try those things. So we always go live right away, and that's very difficult to do.
Carl, a few years back, you have developed very nice technology. And it was really exciting, which is a smart appliance. It's a device that you put that can accurately regulate the power based on a frequency signal, where the customer wouldn't even feel that they have been controlled or curtailed. I think that this was an excellent smart grid device, and you were ahead of the curve. My question is, are you happy with the implementation of that device? Is that device being implemented as you hoped it would be implemented? And if not, what would it take to have it wide spread use?
Good question. It's never fast enough. Actually, it's being embedded in several different activities, both in smart chargers for electric vehicles and in some appliance activities. Water heaters is, I think, the more interesting kind of first application. I think part of the delay, there are two barriers. One, the white goods manufacturers don't have a clue what ancillary services are and how they actually extract financial value from something like that. It's two business models that have never interacted together, so that takes time. And then I think there is still some question. People are trying to understand what does that mean in terms of the performance on the system. Is it going to interfere with some of the embedded controls and other things in the current system? So it's moving forward, and I'm pleased with the progress it's making, but it's never fast enough. But I think it will be tested out in various small applications. My guess is it's probably going to end up in volume more offshore sooner than it is onshore. That's where we're getting more of the interest in the activity.
That's a lead into my question, because something, just an observation and the question. Observation during the day, I've heard local, I've heard regional, I've heard national. I've never heard the word international until that sentence, which is the exact antithesis of almost every other technology and the way it's being spread. So that was a question I had, is do you see, because everybody talking about you move slowly, right, because you have to have this active system. Are there other places where you could do this? Right? So either other places where the technologists will take advantage of their speed, or places where we, by identifying them now, can go in and take advantage of the speed and partner with them. Do you think there's an opportunity for that?
I think there's definitely an opportunity. If you look at the economies that are growing extremely fast, and it's not hard to figure out who those top one or two are, their rate of adoption is extremely high. Our sense is there's still a high level of interest in sort of the innovation that is brought by a lot of the entities here in the U.S. But if you're just looking for just speed, you can do it offshore. Now, for us as a national laboratory, our job is first and foremost to support the American economy and American vendors, et cetera. So that's a bit of a challenge. We have very strong research relationships throughout Asia, mainly in energy storage and with the power system in China and others, and we're working with them on policy issues. And it's very much a part of what I think the innovation needs to be, particularly for most of the vendors here, Schweitzer and also in everybody else. They're in those same markets. So anything, we need to think global. We need to act global as much as we can. It adds a level of complexity that I think for research institutions, it's hard on the business side, but it's pretty easy on the collaborative and the research side. And I know that Anjan spends a good bit of time in China, and we do as well. And so I think from a standpoint of research, it's a great area for collaboration. On the other extreme, the deployment, it's actually going faster there than here. It's a little hard putting together the right business model.
One comment about China and one comment about Europe. China, yeah, things are moving very fast, but their power system is a completely different system than what we are doing here. They are dealing with what we would consider very basic issues that have been solved quite a while back. No, they just need more capacity. That's their main thing. While we are very worried about fine optimization, they are still working in the body of the problem. In terms of Europe, yeah, there's a lot of work going on in Europe, lots of interesting research, but things tend to move a bit more slowly in Europe. They don't have the same entrepreneur culture that can deliver enormous benefits and that we should be able to take advantage of.
Couple real quick comments. One is that, of course, we've mentioned a couple times today that the power systems aren't labs because we depend on them. But we can in this day and age, and it's a great opportunity for the universities, especially working together in the areas of modeling and simulation with the real-time transient simulators and so forth, to be able to model power systems, improve the new technology so that when they do go into a real application, you're sure it's going to work right. Another one is that in addition to the utility power systems, there's all kinds of isolated and smaller ones in refineries, gas oil separation plants, all kinds of process, shipboard things, oil drilling rigs, spars, to the pumping stations. So all kinds of generally isolated power systems like that where we can and have put new ideas to work. And these get, proven out in those environments, and then, they become proven enough that it's easy to adapt to the utility world without much or any risk to the power systems.
Thank you. You want to react to that?
Yes, I think Edith makes two excellent points. In terms of simulation, I think that ties up a little bit with the research idea that Anjan had and I talked about, is developing those tools that can model not just the traditional power system, but also the communication system that goes with it. We need tools that can actually do that. And then your example of the industrial systems is very useful. The United States does not have too many islands where we can do tests, but those are also usually good examples of power systems for where you have real problems and where you can try things with a limited amount of risk.
Can I add one thing on the idea of a simulation lab? And one of the things that has happened in this country over time is many of the large laboratories that the large power companies used to have really been diminished in many ways, mainly because of financial reasons or financial decisions that have been made. And the only place you now see a very large simulation capabilities are out, not in this country anymore. And one of the reasons they can do those kinds of things in a place like China is they'll have the state grid in China actually build this many millions of dollars, hundreds of millions of dollars worth of labs. And that may be one of the national prerogatives that could be taken up by DOE, by the labs, by the utilities all working together, whether you do it regionally or do it differently, but these would become then labs. So even if you can take advantage of actual probing the real system like BPA does by, they've even gone to the trouble of switching on the brake, on the dynamic brake, and take readings. Those kinds of things are good, but you can only do that up to a certain extent. Whereas if you have real simulation labs, that includes all of the new technologies that we have today. I think those are that may be a national prerogative and we have a big history of doing this kind of stuff. I mean, we've done it on the defense side a lot, but even in the where there's a large private sector presence, like in this in the chip industry, we've had rather large labs. I'll recognize you.
Given that we have an opportunity here with the neutral ground, as Anjan and Daniel said in the beginning, and there's an opportunity for, and there is a need for something like a lab that you could do experiments. So my question, particularly to Carl, because you're kind of in the middle between the industry and the academics and see both sides, what's the research agenda that could take what are some of the key questions that could take advantage of such a lab, bearing in mind industry's need and the utilities need for controlling things and maintaining privacy, et cetera?
One of the first things that comes to my mind is the area of energy storage. And in fact, we're talking with Bonneville. They have their laboratories over in Vancouver, Washington, and they put together a kind of a rejuvenation plan for those. And I think the substation is where a lot of new stuff is going to happen. And having access to substations, both lower voltage and higher voltage substations, to test the role of energy storage and new devices, to test some new controllers and other things would be of extremely high value. And as Anjan said, we don't have access to those anymore. PowerTech used to have, I don't think they still have their high voltage lab. Bonneville used to have a very active high voltage lab, and they don't. So that's one piece. The other, I think the important laboratory, if you will, is the consumer side. I think we need to have some very well-structured engagement with consumers at different strata in terms of age and all other dimensions. We found in Olympic Peninsula that those darn retired Boeing engineers were not your typical consumer, because they love to get up every morning and get on the computer and figure out what happened. But I think that if we could find some pockets around the state of ongoing consumer engagement, I think the universities will be an interesting piece of that with what gets put in here over the next 12 months. That would be another, I think, exciting sort of laboratory, if you will, of getting really close connection to consumers and really listening to them and seeing what works for them and how do we do this in a way that sort of delights them.
Yes, and if we go into software labs, I think we have over the last 30, 40 years developed some really good simulation tools for the heavy electrical side of things. I think we can trust those simulations, the tool these days, to give us reliable answers. But this whole other side, the IT side of the system, we don't really know how it behaves, and we certainly don't know how it behaves when it's connected to the actual power system. So if we can have a lab where the two can be connected together, in terms of square feet, it's not going to be very big, but it's going to be quite complex to develop that. And that's going to be absolutely essential to give industry confidence that this kind of stuff can be deployed and it's really going to work as advertised.
One of the things we haven't done, even though we're on a university campus, is talk about the education. We mentioned how the need for new smart grid engineers. So I'm going to turn over the floor to Hardev Judge from BPA on a program that the IEEE Power Engineering Society has initiated for scholarships in electric power engineering. It's a countrywide effort divided up into the regions. Each region is going to take care of the scholars in their region, and so Hardev's in charge of Region 6, which includes us. And so if you tell us a little bit about it and get everybody excited about it.
We got $1 million from IEEE to that trust fund. Finally, it came to fruition, and we are asking applications, and the deadline is June 30th from students. So sophomore will get 2,000, junior will get 2,000, and senior will get 3,000. So professor will give that to the students. So I have the website, and if you go to PES or Power Energy Society website and look for Scholarship Plus, please. And we are the largest region, and we have less number of applications right now. Anjan or Jay, you want to add something?
No, I think it's just starting up, so many of the students don't know about it. We're asking everybody from freshmen up to apply that is interested in power engineering. I think we owe a round of applause for the panelists, and I think coffee is out there.